in this lecture, now we discuss the semi group generated by the heat equation. Now we begin formally the discussion on evolution equations that we mentioned in the introduction. So, we will discuss one by one the heat equation, the wave equation and Schrodinger equation. Before I start the discussion on heat equation, I thought of making a few remarks again on semi group theory. So, these are important. Of course, I have not covered many topics. So, I wanted to leave this also, but somehow felt it is important that I should say something about these three remarks. Okay. So, now some remarks. So, again on semi groups. So, the first one is with regard to inhomogeneous abstract Cauchy problem. So, namely this ODE in a Banach space. So, now we are adding an inhomogeneous term and U0 is in X. So, if A generates a strongly continuous semi group, so now this F is from 0 infinity into the Banach space. Okay. So, with suitable conditions on continuity, differentiability, whatever is needed. Okay. If A generates a strongly continuous semi group, T T. So, then we can write down the solution of this inhomogeneous equation, then U of t is T T of x 0 to t, t of t minus s okay. So, for x in domain of A. So, this is nothing but Duhamel's principle. Okay. So, this is the first remark, and the second one concerns with dual semi group. In fact, we need this in the proof of Stone's theorem. So, let me the easier one first let T T be a. So, let me now stress that strong continuity be a strongly continuous semi group in a Hilbert space. So, the advantage of working in a Hilbert space is that the dual operators. So, these are all TTs are bounded linear operators on H. So, the duals the adjoint, not dual, the adjoint operator is also defined on the Hilbert space. Okay. Then you consider this family of adjoint operators. The family of adjoint operators T star T. Okay, so this. So here I am just T star T is nothing but the adjoint of T T. Okay, just. So it's easy to check that the T star T satisfy the semi group property. There is no trouble with that. But what's important is that this T star T. So this is T star T is also a strongly continuous semi group so let me say this is H, okay. Continuous semi group in H and its generator is a star where so A is the generator of T T. Okay. So, in other words, in a Hilbert space, if we have a strongly continuous semi group T T, then the family of adjoint operators also forms a strongly continuous semi group, and its generator is nothing but the adjoint of the generator of the semi group we started. Okay. So, this so of course, this is not an easy proposition. So, one has to do some work, and the only advantage here is that T star T is also defined on H. Okay. So, in a general Banach space this is also true, but with some modification. So, that is what I now remark. So, let T T be a strongly continuous semi group in a Banach space X with generator A. So, let me write that. Okay. Now, the family of adjoint operators T star T but now this is in B X star. So, they are defined on the dual space. X star is the dual space. Of X. So, obviously, there is no trouble with semi group property again, but there is in general T star T is only weak star continuous. So we lose this strong continuity. Okay. So strong continuity means what? So norm of t t x minus x tends to 0 as t tends to 0 for all x. That is strong continuity. But in this case we have only weak star continuity, that is, so let me just say that. So if this is the duality bracket between x star and x, so you have this t star t, you take an x star in the dual space minus x star. So this is the duality bracket between x star and x, and this tends to 0 as t tends to 0 plus for all x star in the dual space and x in the original Banach space. Okay. And this gives, so I will not further emphasize. So this generator, so of t star t, again that is defined only in the sense of weak star topology. Okay. So call it A star. So this is weakly closed, weak star closed, and this dA star is also weak star dense. So in case of strong continuity we have seen that dA is strongly dense, but here we can only say that. Okay. So this is the general situation, but everything is fine once we put extra conditions on x. So if x is reflexive, there is absolutely no problem. So x is reflexive, then t star t is again a strongly continuous semi group. Continuous semi group with generator A star. So now A star is a closed operator in x star and its domain is also dense in x star, but that requires x to be reflexive. So just to reflect this thing, so here is an example. Okay, so now you consider this x L1 R. So we so this is not a reflexive Banach space. So we identify its dual with L infinity R, right, and consider this semi group of left translations. Consider T T. Now it is in fact it is a group. Okay, so no problem. So T T of f at x. So this is f of x plus t. So f is in L1 of R. So x is in R, t is in R. So we have seen earlier that this is a strongly continuous semi group. So its generator is the derivative. Okay, so that's. So what about the adjoint in fact group? This is it's a group. So adjoint Okay. Adjoints now are defined on x star, that is L infinity R. So, you can easily check that. So, this is just f of x minus t. Okay. So, this f is in L infinity R and x t r in R. Okay. So, you can check that t star t is only weak star continuous. Okay. In fact, there exists f in L infinity such that this L infinity norm minus t minus f of. So, this in L infinity does not go to 0. Okay. So, for example, you can try this. Okay. In fact, very nice functions f of x equal to sine of x square. So, this is a continuous bounded function. Check whether this this does not hold. Okay. So, and the third remark, these are all important topics, but unfortunately no time to discuss. So, the third remark is concerning holomorphic or analytic semigroups. So, this is a special class of semigroups. So, I am not going to define what that is, that will take much more time. Just say that so if you start with T T, so this is only defined for T non-negative, that is on the positive axis. So, when we can extend the definition of T T to a small wedge in the complex plane, that will result in holomorphic semigroup. One important property I would like to say about this holomorphic semigroups, and in fact, the semigroup generated by the heat equation had this property. So, we have seen that. So, if T T is a strongly continuous semigroup, so if x is in d A, then T T of x is also in d A for all t non-negative, and we have this relation A of T T x is equal to T T of A x. So, in general, for x in just in the Banach space, so we cannot claim that T T x belongs to d A. Okay. So, but for holomorphic semigroups, that is what happens for x. So, this T T x may not for T positive. Okay. So, for holomorphic semigroups, so that is what happens for holomorph. So, they are in fact characterized by this, one of the characterization holomorphic semigroups. We have T T of x belongs to d A for all t positive and x in x, that is important. Okay. So, in the application to PDE, what this means is the solution is smooth for T positive, and that is what we have seen in the case of heat equation. Okay. So, with these remarks, now I move on to this heat equation. Okay, so, this is du by dt. So, assume we have absorbed all the constants arising the heat equation in T. So, this is in x in Rn and T positive, and with some initial condition. So, at least in the case when f is bounded and continuous, we have seen this is classical thing, the solution when f is smooth. So, let me write that way, the smooth and bounded. The solution is given by the Fourier Poisson formula. So, if you have not seen it, refer to our book on PD, that is classical theory, Fourier Poisson formula. So, u of x t, so let me just write that. So, this k t convolution with f at x. So, this is t positive and x is in Rn. So, k t is the Gaussian or fundamental solution of the heat equation. Okay, so, where k t of x 4 pi t minus n by 2 e to the let me write minus mod x square by 4t. So, this is for t positive. So, this u satisfy the heat equation, and u also satisfies the initial condition in the sense of limit. So, that at t tends to 0, u x tends to f x, at least when f is smooth. Okay. So, now we take this at the starting step and define this semi group. So, this is the semi group generated by the heat equation. Okay. So, define so let me use a different letter W in LP Rn. So, again 1 is less than equal to p less than infinity by. So, Wt acting on a function f in Lp. So, we have to mention what its value at x is. So, this is precisely given by Kt. So, this is for t positive and x is in Rn, and we put W0 of f equal to f. Okay. So, this for f in LP Rn. Okay. So, two important properties we constantly use about Kt is that Kt is a positive function and integral Kt x dx in Rn. Okay, so let me, so even if I forget to write, so in this lecture I have in the discussion on heat equation it's over Rn. Okay, in fact all the equations we only deal with in Rn. So this is Kt x minus y dx. So here for all y, and this is again Kt x minus y dy. This is for all x, all are equal to 1. And for t positive, so in fact this Kt is in the Schwarz space. Okay. So the first proposition, that's the somewhat easier one. Wt is a strongly continuous contraction semigroup. Okay, so that's the first proposition. Okay, so let me give some details so that you also start working with more examples. Okay. So first let's prove the semigroup property. So that's somewhat easier. Semigroup property. Okay. So if you take T1, T2 positive, then this Wt1 of Wt2 F is in LP. So this is by definition. So Kt1 star Kt2 star F, and by associativity, so this is Kt1 star Kt2 star F. And here comes an interesting property of the heat kernel. So you can, so this, since these belong to Schwarz class, we can use Fourier transform to compute this convolution, and you find that this is precisely Kt1 plus, and that's by definition Wt1 plus T2F. Okay, so this is for all F in L. Okay. So next, the strong continuity. So next, let F in LP Rn. So we have this WTF at x is Kt star F. So let me write that. Okay, let me not write that. So that's, let me not write that. So, k t star f. Okay, you write that integral and other things. So, you take the absolute value, okay, and then you 1 power p. Okay, so, this is precisely integral k t x minus y f of y to the power p dy. Okay. So, when p is equal to 1, this is almost immediate, and for p bigger than 1 you use Hölder's inequality. Okay, so, this is less than or equal to. And now you integrate with respect to integrate both sides with respect to x. X and use Fubini. So, in order to get that WTF in LP is less than or equal to. So, here we are using constantly these two properties. Okay. So, that especially the integral kt is positive. So, we do not have to put any absolute value there, and integral kt is 1. So, that is very important. So, this immediately shows that Wt maps LP to LP Rn, okay, and norm of. So, it is continuous. So, that is the first step. Okay. So, it remains to show that. So, next is strong continuity. Okay. So, this is bit delicate. So, let me continue this in the next lecture. Okay. Thank you.